Hi everyone, my name is Zhang Mingkai from Tongzi Sanjia. Today I'm going to report the data mining final. And this is my final report content. And the data set contains 20,174 records and for 15 variables, focusing on healthy related data for children under 18 years. The target variable is panel, which represent group classification with 8 distinct categories ranging from 0 to 7. The dataset was sourced from a public repository, providing insights into various healthy indicators. For more details, refer to data's link. And this is my dataset. And during dataset preprocessing, missing value in estimates and SE were replaced with their medians and maintain data integrity. Redundant columns including STUB name, panel num, unit num, and other were removed to focus on relevant features. Continuous variables like estimate and SE were discretized into 5 equal frequency bins using Qcode, improving segmentation and interpretability. And label encoding was used for variables such as indicator panel, year, STUB label, and unit. The primary reason for choosing label encoding was its simplicity and the efficiency for variable with an ordinal or nominal nature, where no additional binary columns were necessary. And one-hot encoding edge was encoded. One-hot encoding it captures categories distinct without introducing any unintended numeric secret. To prepare the data for modeling, the dataset was split into training and test set, with 80% of the data allocated to training and 20% to testing. This split ensures that the model is trained on majority of the data while preserving a separate dataset for validation. The class imbalance in the target variable, often problematic in classification tasks, was addressing using SMART. SMART generates synthetic samples for underrepresented classes in the training data, improving the model's ability to generalize across all classes. Then two feature selection methods were implemented to improve the model's performance by identifying the model's performance by and identify the most relevant predictors. The chi-square test identified 5 key features: STUB label, estimate SE, 0 to 4 years, and under 18 years, resulting in an accuracy 39.79%. Model-based feature selection approaching using a feature importance from a decision tree identified 3 key feature, year, estimate, SE, and achieve accuracy of 40.23%. The comparison between 4 variable and select feature models reveal the effectiveness of feature selection. The 4 variable model achieved a training accuracy of 41.22% and a testing accuracy of 35.88% with a tree depth of 9 and 39 leaf. In contrast, the chi-square select feature model achieved a test accuracy of 39.79% and the model-based feature selection achieved 14.23%. And this is our MI decision tree. To ensure the model's robustness and the generalization, a fivefold cross validation was performed. The decision tree model was evaluated on multiple data subsets, providing an average accuracy of 30.25% across the folds. Uh, and on this slide with association rule, we focus on preparing steps taken before running the association rule mining. First, several columns on refer, such as indicator, STUV name, and their numeric variant, because they are either duplicates or less relevant for our analyst. We then transform the panel variable into two groups, group 1 and group 2. By recording its original factor levels, the conversation helps simplify the classification targets for the rule mining, making it easier to interpret whether the record falls into one group or the other. Additionally, we discretize estimates and SE into 5 bins, each using the equal frag method from the InfoZero package. And here we highlight the R code that implements association rule mining with a rules package. The a priori function is used to discover patterns in preprocessed datasets, focusing on rules that predict panel binary, either group 1 or group 2. In our parameter list, we set a minimal support of 0.09, a minimal confidence of 0.5, and restrict the rules to have at least two items. We examine the most informative rules that survive the pruning process. The table displays critical metrics such as support, confidence, coverage, lift, and the count for each rule. These statistics guide us in understanding how often a rule appears in a dataset, how reliability it predicts its outcome, and whether it provides information beyond random chance. For instance, if estimate equal 5 panel binary equal group 2 demonstrates high confidence and a notable lift, it suggests that we estimate its category as 5. There's a strong likelihood of being group 2. And this part we're talking to SVN and apply to the numeric feature estimate and SE, divide them into 5 equal frequency bins and use for categorical variables such as panel and year, transform them into numeric labels, and apply to the age variable, creating separate apply to the age variable, creating separate binary columns for each category. Implement on numeric features like estimate and SE to normalize them to standard regression distribution, ensuring balanced input magnitudes for the SVM models. This slide illustrates the training and testing strategy along with the implement of SVM model. The dataset was split into 80% for training and 20% for testing, maintaining a consistent random step of 2025-1018for reproducibility. For the non-linear SVM, various combinations of C and gamma were tested. And the performance metrics of SVM model used in analysis. Two variations of SVM were tested: the nonlinear SVM with an RBF kernel and the linear SVM. Different values of parameters C and gamma were experimented with to optimize performance. The nonlinear SVM with C equal 0.8 and the gamma equal 0.5 achieved a training accuracy of 45.56% and a testing accuracy of 36.61%. For the linear SVN, the training accuracy was 31.48%, while the testing accuracy was lower at 96%. Additionally, the final turn tuned SVN model achieved a training accuracy of 45.42% and a testing accuracy of 38.25%. The weighted F1 score for the final model was 0.4433, reflecting its performance across all classes. In this analysis, we used a random forest model was constructed after preprocessing the dataset. Feature estimate and SE were discretized into 5 equal frequency bins to enhance model interpretability. The categorical features panel and year were encoded using label encoder, while edge was 1 hot encoding to create binary variables for each category. Unlike SVN, standard scaling was not applied, as random forest models are insensitive to feature scaling, making it computationally efficiency and maintaining data integrity. The dataset was split into 80% training and 20% testing data using a fixed random seed for reproducibility. Multiple random forest model was trained with varying hyperparameters such as earn estimates and max depth to evaluate their impacts on model performance. The provided Python code demonstrates the implement of these configurations. Each configuration's accuracy on both training and testing dataset was recorded to identify overfitting and underfitting trends. The model performance comparison highlights the training and testing accuracy of different random forest configuration. The third configuration with an estimate equal 100 and max depth equal 8 achieve the best balance between training 50.02% and a test 35.70% accuracy, indicates its suitability for a dataset. And then we talk the KNN. We highlight the key pre-processing steps applied to our dataset before fitting a KNN model. First, we discretize the numeric variable estimate and SE using QCut. This process brings the continuous values into a fixed number of categories. Next, we use label encoder to transform categorical features like panel and year into integer label. For edge, we apply 1 hot encoder. And finally, we standardize year estimate and SE with standard scaler, which centers each feature around the mean of 0 and scales it into unit variance. Here we demonstrate how we split our data into training and testing sets, and how we determine the optimal number of neighbors for K for the KNN algorithm. By using train test split with 20% test size, we ensure an unbiased evaluation of model's performance. We then construct a loop from 1 to 200 neighbors, training a KNN model for each value of K. Within each iteration, we calculate both training accuracy and test accuracy via accuracy score. The scores are stored in spreadsheet list so that we can track how performance varies as K changes. And we present the outcome of our model when using the best K value, which we found to be 74. The testing accuracy K equal for 74 reaches approximately 38.25%, while the training accuracy is about 48.20%. This gap indicates that the model generalizes modestly So there is still a noticeable difference between two accuracies. And here we don't demonstrate how to combine our individual cluster random forest KN and SVC into an ensemble using 14 classifier. By specifying soft 14, each model contributes its predict probability for each classes, and the final prediction is based on average probability. In contrast, hard 14 strictly counts the majority case predicted by each model. In a code snippet, we see how each classifier is first trained on the same training dataset, then they are passed into two 14 classified objects. And we compare 5 machine learning models, decision tree, SVN, random forest, and KN and 14 ensemble based on their training and testing accuracy. Among these models, 14 achieves the highest test accuracy at around 38.98%, surpassing any single estimator. And in this slide, we talk about K-means. We highlight how we determine the appropriate number of cluster for our K-means analysis and examine the corresponding classification accuracy when using those cluster as label. The elbow plot on the left show the sum of square errors (SSE) decreasing sharply as the number of clusters increase. Then beginning to flatten around this 3 to 6 cluster, we test k equals 3 and k equals 6 in detail. Here we present a closer look at the k-means cluster defining characteristics and the possible interpretations. Each cluster is described by its estimated AC, various age-related features, and panel values. For instance, cluster 1 has notably higher estimate, moderate SE, and strong representation in panel, possibility indicating a group with larger estimate value but manageable error. In summary, after evaluating multiple models on both training and testing sets, Soft14 achieved the highest test accuracy and its advantages were clearly supported by the data. By integrating various algorithms such as SVC, KNN, and random forest and 14 based on their predict probability, Soft14 effectively might get biases from any single model while accommodating diverse feature spaces. This leads to more robust and superior predictive performance in real-world application. The conclusion is not just theoretical, but is grounded in through data analysis and comparative experiments. Thank you.